All right, so welcome back to our SPI Doppler review series. This is phase 3, hemodynamic equations. And now that we've examined how blood moves through different flow patterns, we're ready to explore why it moves that way. In this episode, we focus on, again, phase 3, hemodynamic equations. And this is where the physics behind flow becomes clear. We'll break down the continuity principle, um, Poiseuille's law, and Bernoulli effect. So the governing rules that explain velocity changes, resistance, pressure differences, and vessel diameter relationships. So understanding these equations is essential because Doppler doesn't just measure motion, it reflects the physics driving that motion. When you grasp how pressure, radius, and flow rate are mathematically connected, SPI questions shift from memorization to logic. So let's move from observing flow patterns to understanding the forces that control them. Now that we've worked through flow types, let's zoom back out and look at the full progression of phases. So we began with fluid basics, understanding what blood is as a fluid and what allows it to move. Then we moved into flow types, where we examine how blood moves, laminar, plug, pulsatile, disturbed, turbulent patterns. And that gave us a visual and conceptual understanding of velocity and velocity distribution within those vessels. Today we transition into phase 3, which is the hemodynamic equations. So if flow types describe the patterns we see, hemodynamics explains why those patterns occur. And this is where pressure gradients, resistance, vessel radius, and flow rate are connected mathematically. Continuity and Poiseuille's law and Bernoulli's effect give us the physics that govern those flow behaviors. So once we understand hemodynamics, we're prepared to step into Doppler physics, where motion becomes frequency shift. And from there, we'll explore signal processing, then instrumentation, and finally, clinical application, where everything comes together in real diagnostic scenarios. Each phase builds logically on the previous one, and right now we're focusing on hemodynamics, the physics engine behind blood flow. So now we enter phase 3, hemodynamics and equations, where physics begins to govern everything we've discussed so far. So flow types describe, again, what blood is doing. Hemodynamics explains why it behaves that way. And so over the next several slides, we'll build this step by step. First, we'll define volumetric flow rate, what it actually means when we say flow. Then we'll look at the formula for volumetric flow rate, connecting velocity and cross-sectional area. From there, we'll examine the continuity rule, which explains why velocity changes when vessel diameter changes. Next, we'll analyze what happens when pressure increases and how pressure differences drive flow. And we'll move into resistance, specifically how resistance depends on radius to the fourth power. This concept is critical and heavily tested. That leads us into Poiseuille's law, where diameter becomes the dominant factor controlling flow. After that, we'll discuss Bernoulli effect, explaining how velocity and pressure are inversely related. And finally, we'll anchor everything with the maximum normal flow speed in the circulation, giving a clinical reference point. So this entire section is designed to build your main for Doppler, because once you understand how pressure, radius, resistance, and velocity are mathematically connected, Doppler questions stop being random and they start becoming logical. Okay, so the next question here is the amount of blood passing a point per unit of time defines what? And the answers are A, velocity, B, viscosity, C, resistance, or D, volumetric flow rate. So the correct answer here is D, volumetric flow rate. This is the amount of blood passing a point per unit time. And it's the definition of flow, which is equal to volume divided by time. We can express this as milliliters per second or liters per minute. And this volumetric flow rate tells how much blood moves past a location each second, not how fast it's moving. And let's talk about why the other answers are wrong. Let's break these down. So the first one, A, says velocity. And again, velocity is some distance over time. So centimeters per second or meters per second. And velocity tells you how fast red blood cells are moving. Flow tells you how much blood is moving. So it's a big difference. You can have high velocity in a narrow vessel, but low total flow. So velocity does not equal flow. Answer B was viscosity, and this is wrong because viscosity again, is a thickness or internal friction of blood. It affects resistance, but it is not a measure of blood amount per time. Honey has a high viscosity, water has a low viscosity, and neither describes flow directly. The last one was resistance, and again, this is wrong because resistance opposes flow. So it is defined as resistance being equal to a difference in pressure over flow, which resistance affects flow, but it's not the definition of flow. And so the key concept here that you have to know is that flow depends on velocity times area or cross-sectional area. And so that's why when we look at capillaries, they have low velocity but large total flow. And when you think of stenosis, this has high velocity but reduced flow. And this is a major concept in Doppler. Okay, so the next question is the volumetric flow rate is equal to blank. And the answers shown are A, pressure difference multiplied by the resistance, B, resistance of blood flow multiplied by the flow rate, C says the average flow rate across the vessel multiplied by the cross-sectional area, and D is the force per unit area. And of course, the correct answer would be C, average velocity times cross-sectional area. So volumetric flow rate is defined as Q is equal to A times V, and Q is equal to the volumetric flow rate, A is the cross-sectional area of the vessel, and V is the average velocity across the vessel. This tells how much volume of blood passes through a vessel per unit of time. So if the vessel is wide, more volume can pass. If the velocity increases, more volume passes per second. So this answer is literally the definition of volumetric flow rate. Now let's look at the others and determine why they are incorrect. So the first one was A, pressure difference times resistance. This is incorrect mathematically and conceptually. The real relationship is Q is equal to delta P over R. So the difference in pressure over resistance. Flow equals pressure difference divided by resistance, not multiplied by resistance. So in fact, if resistance increases, flow decreases. So multiplying by resistance would suggest the opposite. So this answer reverses the physics basically. The next one is B, where it says resistance times flow rate. So this doesn't even define flow. It just rearranges variables without meaning. So also, if you look at the formula, delta P, which is the difference in pressure, equals to Q times R. Resistance times flow rate equals pressure difference, not flow. So this describes pressure, not volumetric flow rate. And the last answer that was incorrect was D, force per unit area. This is a definition of pressure, that's all. So pressure is equal to force divided by area. It has nothing to do with defining volumetric flow rate. Okay, so this question asks, blank describes the volumetric flow rate as a constant. And the answers are A, Bernoulli's effect, B, continuity rule, C, viscosity, D, Poiseuille's law, and which should be E again, but it says D there twice, the Doppler equation. So the correct answer here would be B, the continuity rule. So let's just recap. The continuity rule or continuity equation states that flow is equal to area times velocity, and in a closed system like a blood vessel without any leaks, volumetric flow rate remains constant. So if the vessel is narrow, area decreases, velocity must increase. So that flow Q stays the same. That's why blood speeds up in stenosis. So the key idea is that continuity equals conservation of mass, which equals constant volumetric flow rate. Now let's look at the other answers and see why they're incorrect. So A said the Bernoulli effect. So Bernoulli describes a relationship between pressure, velocity, and height. It explains why pressure drops when velocity increases. It doesn't state that the volumetric flow rate is constant. So Bernoulli is about energy conservation, not about mass conservation. And the next one, C, Poiseuille's law, I'm trying to say this correctly in the French. Poiseuille's law describes that flow is proportional to pressure times the radius to the fourth power divided by the viscosity times length. So what this tells us is how that affects flow, especially how dramatically radius impacts it. So it doesn't state that flow is constant. So in fact, Poiseuille's shows that flow changes when resistance changes. The next one, D, is the Doppler equation. So the Doppler equation calculates velocity from frequency shift, and so it measures flow characteristics. It does not describe conservation of volumetric flow. So there's a big concept difference. So continuity relates to conservation of mass, which relates to constant flow. Bernoulli relates to conservation of energy, which relates to the pressure over the velocity relationship. Poiseuille's relates to resistance factors that affect flow. And then Doppler relates to velocity measurements. So when you see volumetric flow rate remains constant, your brain should immediately think the continuity equation. Okay, so the next question is, if pressure differences in a straight vessel increase, the flow rate does what? A, increases, B, decreases, C, does not change, or D, changes direction. And the correct answer here would be A, it increases. So if delta P, that pressure difference, goes up and resistance stays constant, flow increases. So more pushing force relates to more blood that moves per second. It's like turning up the water pressure in a hose, so you have more water that flows out. Flow and pressure differences are directly proportional. Next is, why are the other ones wrong? Let's start off with B. So decreases flow would only decrease if resistance decreased. I'm sorry, if resistance increased or pressure difference decrease. You can look at this just by looking at the formula. So the question clearly says pressure difference increases. So decrease makes no physical sense here. The next one is C. Why is this wrong? Does not change flow, or does not change. So flow only stays constant if pressure and resistance remain constant. Since pressure difference increase, the flow must change. So this option ignores the fundamental relationship. And the last one, D, changes direction. So flow direction depends on which side has higher pressure. Increasing the pressure difference does not reverse direction. It just strengthens flow in the same direction. So blood flows from high to low pressure. If the high gets higher, it flows more strongly, but not backwards. So this question asks, resistance of the blood flow depends on the radius of the blank. So the answers are A, tube to the fourth power, B is tube squared, C is tube divided by the length of the tube, and D is just tube. So let's look at these one by one. So the correct answer is going to be A, tube to the fourth power. So Poiseuille's law tells us that the resistance is proportional to 1 over the radius raised to the fourth power. So resistance is inversely proportional to radius to the fourth. So this means that if radius decreases just a little, resistance increases a lot. If radius doubles, resistance drops dramatically. So this is why a small change in vessel diameter, like stenosis, has massive effects on blood flow. That's the fourth power is the key thing here, and the denominator. So B says tube squared, and that's a big no. It's not squared. If it were squared, changes in radius would matter, but not nearly as dramatic, right? So the fourth power makes radius the most powerful factor affecting resistance, and this underestimates how strong the radius effect really is. The other answer that's incorrect is C. So tube divided by length of the tube. So Poiseuille's law actually says that resistance is proportional to the length divided by radius to the fourth. Right? So length is in the numerator and the radius to the fourth power, that's in the denominator. And this option mixes concepts incorrectly and doesn't reflect the correct relationship. Again, the last answer, D, which is also incorrect, that's just too vague. So yes, resistance depends on vessel characteristics, but the question specifically asks how resistance depends on radius. So the mathematical relationship must be specified. So just saying tube doesn't answer the power relationship. So this question asks, Poiseuille's equation states that if the flow rate increases, the blank, right? And the answers are A, the tube length has increased, or B, tube diameter has increased, C, pressure difference has decreased, or D, viscosity of the fluid has increased. Now I know that the answer is highlighted there on the slide, and again, I don't have a copy of this image without it right now, but the correct answer you can see there is B, tube diameter has increased. If we look at the equation, Poiseuille's equation, flow is equal to delta P times pi times radius to the fourth, all divided by 8 n times L. And so Q being the flow rate, delta P is that pressure difference, R is equal to the radius. That little N sign is viscosity, and then the L is the tube length. And again, the key player here is R to the fourth. The flow rate is proportional to radius to the fourth power. So that means, again, if radius increases just slightly, flow increases dramatically. If diameter increases, therefore the radius increases, so flow will increase. So flow rate increases. The most powerful explanation is the tube diameter has increased. And why are the other answers wrong? So let's take them one at a time. A says the tube length has increased. So flow is inversely proportional to length. So Q is inversely proportional to 1 over L. So if length increases, flow decreases. That's how inverse proportionality works. It's opposite. The next one is C. There's a pressure difference that's decreased. So again, flow is directly proportional to pressure difference. So Q is equal to delta P. It's proportional to delta P. So if pressure differences decrease, flow decreases. So again, this one's not correct either. And then the last one, D, viscosity has increased. So flow is inversely proportional to viscosity. So Q is inversely proportional to 1 over the N, which is the viscosity. So if viscosity increases, flow decreases. Again, opposite effects. And so a mental image or shortcut is when you see Poiseuille's radius is what rules everything. So increased diameter, massive increase in flow. And that's a dominant factor in the equation. Again, Poiseuille's law, Poiseuille's equation. Trying to say it in the correct French pronunciation. Okay, so let's look at this next question. The decreased pressure in regions of high flow speed is called what? A, Poiseuille's law, B, Bernoulli's effect, C, continuity rule, or D, volumetric flow rate. And the correct answer there, was just partially highlighted, is the Bernoulli effect. So the Bernoulli principle states that as the velocity of a fluid increases, the pressure within that fluid decreases. So in simplified form, it's inversely proportional. So velocity goes up, pressure goes down, assuming height stays constant. And that's why, like in a stenosis, or we have vessels that narrow, velocity increases, pressure drops, and that drop in pressure is at high velocity or in high velocity regions. This will be due to the Bernoulli effect. And this is clinically important because we estimate pressure gradients across valves using Doppler, and we look at high velocity jets that correspond to pressure differences. Now let's look at the other answers and determine why they are not correct. So A says Poiseuille's law. And so Poiseuille's law describes, again, how flow depends on pressure difference, radius squared, viscosity, and length. It explains resistance and how radius dramatically affects flow. But it doesn't describe pressure dropping because velocity increases. That's a different principle. The next one is C, the continuity rule. So the continuity rule says that Q is equal to A times V. So if area decreases, velocity increases to keep that flow constant. Continuity explains why velocity increases in an arid region, but it doesn't explain why pressure decreases. Bernoulli explains the pressure change. So students often mix these two, and exam writers love this to throw you off. The last one is D, the volumetric flow rate. So volumetric flow rate designated by the letter Q. This describes how much volume moves per unit time, and it has nothing to do with the pressure dropping in high-speed regions. It's just a measurement, not a principle explaining energy changes. Energy changes. Okay, so this is going to be the last question for this section, or for this phase. The question is, the maximum normal flow speed in the circulation is blank centimeters per second. And the options are A, 75 centimeters per second, B, 80 centimeters per second, D, 100 centimeters per second. I'm sorry, C, 100 centimeters per second, and D, 125 centimeters per second. And so the correct answer here is C, which is 100 centimeters per second. The maximum normal flow speed in systemic circulation, typically referring to the aorta or the major arteries, is about 100 centimeters per second, and that's approximately 1 meter per second. So in large arteries like the aorta, peak systolic velocities are commonly in the range from 80 to 120 centimeters per second, around 100 centimeters per second, and that's considered the normal upper value. So 100 cms per second is the best normal choice here. And why are the other answers wrong? So again, A says 75 centimeters per second, and 75 is normal for some peripheral arteries, moderate arterial flow, but it's not the maximum normal in the circulation. It's too low to represent peak arterial velocity. B says 80 centimeters per second. So again, the same issue we have that we did before. 80 cms per second is still within normal range, arterial range, but not the maximum normal value. It underestimates peak systolic velocity in the larger arteries. And D says 125 centimeters per second. And so this starts getting into the upper limit territory. So possible mild elevation, potential early stenotic values, and this depends on the vessel. So it can be seen in normal individuals. It's higher than the standard maximum normal value that's taught though. So conceptually, think of it like this. Capillaries, very slow rate, about 0.1 to 1 centimeters per second velocity. And then veins are slower than arteries. Large arteries are the fastest, and peak systolic in major arteries is about that 100 centimeters per second. And think of that and hold on to those numbers and make it like a mental benchmark so when you answer further questions in this area. I want to thank you very much for your time, and I will see you on the next phase.